Welcome to part 10 of our ANSYS Fluent tutorial series. We're so glad to have you here as we continue working on our second project, simulating a vertical axis wind turbine, VAWT. Before we dive in, don't forget to like, leave a comment, and subscribe. Your support really helps us stay motivated and continue creating valuable content for you. Now, let's pick up right where we left off. In this part, we'll focus on setting up the cell zone conditions for one of the turbine blades. First, go to Cell Zone Conditions, select Fluid Blade XNEG, and click Edit. You'll notice that air is already set as the material, so no changes needed there. Now, enable the Frame Motion option. This activates the Moving Reference Frame MRF model, which lets us simulate rotational effects even in a steady-state solver. Set the rotational axis origin to -1, 0. This defines the axis of rotation 1 unit to the left of the center. Enter 2 radians per second as the rotational velocity. For relative to, select Fluid Rotating Core, so this blade rotates relative to the rotating core zone. Finally, click OK to apply the settings. With this setup, we've correctly defined the blade's rotational behavior using the MRF method, and we're ready to move further into the CFD simulation. Now let's complete the setup by applying the same settings to the remaining 3 blades in our vertical axis wind turbine VAWT model. We're assigning each blade its own rotation around a local axis, located 1 meter away from the turbine's center, the global or hub axis. And keep in mind, each blade rotates at 2 radians per second, which is half the speed of the outer rotating core. Here's what you need to do. 1. For Fluid Blade Expose, Axis Origin, 1, 0. Rotational speed, 2 radians per second. Relative zone, Fluid Rotating Core. 2. For Fluid Blade WNEG, Axis Origin, 0, 1 rotational speed, 2 radians per second. Relative zone, Fluid Rotating Core. 3. For Fluid Blade IPOS, Axis Origin, 0, 1 rotational speed, 2 radians per second. Relative zone, Fluid Rotating Core. All blades now have their own local rotation defined correctly. This setup simulates how individual blades behave in a real VAWT system, rotating around their own axis while being mounted on a larger rotating hub. Let's continue right where we left off and move on to setting up the boundary conditions for our vertical axis wind turbine simulation in ANSYS Fluent. First, we define how the wind enters the domain. Velocity inlet, VIL inlet wind, navigate to problem setup. Boundary conditions, select Veliantrel inlet wind and click Edit. Set the velocity magnitude to 10 meters per second. Under turbulence, choose Intensity and Length Scale. Enter 5% for turbulence intensity and 1 meter for turbulent length scale. Click OK. This simulates wind entering the domain with realistic turbulent behavior. Pressure outlet wind. Now, select Pressure Outlet Wind and click Edit. Set the gauge. Pressure to 0 Pascal. Again, under turbulence, choose Intensity and Length Scale, set turbulence intensity to 5% and turbulent length scale to 1 meter. Click OK. This ensures a smooth and realistic outflow of air from our domain. All right, let's now move forward and define how the walls of the blades behave in our CFD simulation. This is an important step because, in rotating systems like a vertical axis wind turbine, VAWT, wall motion significantly influences the near-wall flow behavior and shear stress, which in turn affects the aerodynamic forces on the blades. Setting rotating wall motion, head over to Problem Setup. Then Boundary Conditions, double-click on Wall Blade Xneg. In the new window, under Wall Motion, change the type to Moving Wall. Then, under Motion, select Rotational. Keep the speed at 0 rad per second relative to the cell zone. Why are we doing this? Even though the actual rotational motion is already defined in the cell zone settings, the solver also needs to be informed about the wall's motion relative to the mesh. By choosing rotational motion with 0 radians per second relative to the cell zone, we are telling ANSYS Fluent. The blade is rotating along with the mesh it's inside, so from the mesh's perspective, the wall isn't moving. This approach ensures Fluent can correctly model the shear forces acting on the blade surfaces. Also, take a look at the second line of the panel, where you'll see a grayed-out field indicating which cell zone this wall belongs to. It confirms that this blade wall is tied to the correct rotating cell zone we configured earlier. Now that we've set up the boundary condition for one blade wall, it's time to speed things up by copying those same settings to the remaining blade walls. Instead of repeating the entire wall motion setup manually for each blade, Fluent allows us to copy boundary conditions from one zone to multiple others. Perfect for cases like this, where the blades are symmetrical and require identical settings. How to do it? Go to Problem Setup. Then Boundary Conditions, click on the Copy button located in the toolbar. In the Source Zone field, select Wall Blade Xneg, the one we already configured. In the Target Zones field, hold Ctrl and select Wall Blade Xpose, Wall Blade Weneg, Wall Blade Ipose, click Copy. Then OK to confirm. Why this step matters. This method ensures that all blade walls share the exact same motion behavior, which is essential for maintaining simulation consistency and symmetry. It also saves time and reduces the chance of manual errors. In this part of our setup, we'll configure the solution methods, a crucial step that determines how the governing equations of fluid flow are numerically solved in ANSYS Fluent. Go to Solution, then Methods, under Momentum and Turbulence Equations, select Second Order Upwind. For the Pressure-Velocity Coupling Scheme, select Simple. Now retain the default values. Why we use Second Order Upwind? Second Order Upwind is more accurate than First Order Upwind because it uses information from neighboring cells to better estimate variable gradients, especially important when the flow is highly convective. Accurate gradients, like in momentum or turbulence, are crucial. The mesh is fine enough to support higher-order schemes. It provides better resolution of boundary layers, flow separations, and vortices, all essential when simulating complex flows, like those in a vertical axis wind turbine, VAWT. When to use other schemes. First order, upwind. Use for initial iterations to ensure stability, less accurate, introduces numerical diffusion, often replaced with second order as the solution converges. Quick scheme, a higher order scheme, mainly for scalar transport, like temperature. Ideal for structured meshes and smooth gradient flows, can cause instability in complex geometries. Third order. Muscle, very accurate, used in transient simulations, great for shock capturing, compressible flows, or wave dynamics. Computationally expensive, not usually needed for steady-state VAWT. When we use different kind of pressure scheme, 1. Simple. Semi-implicit method for pressure-linked equations. Best for steady-state flows. Widely used for engineering simulations, robust and stable. 2. Simple C, simple consistent. A faster converging variant of simple, useful when the solution is well behaved, and faster convergence is needed. 3. PISO, pressure implicit, with splitting of operators, designed for transient simulations. Ideal when the time step is small, or when simulating time-dependent phenomena. 4. Coupled scheme, solves momentum and pressure together. Much faster convergence, used for compressible flows, or simulations involving strong pressure gradients, computationally more expensive, sometimes unstable for steady-state cases.
In this step, we're setting up the initial conditions for our simulation, the starting point from which ANSYS Fluent begins solving the equations. Go to Solution, then Solution Initialization. Set the initialization method to Standard Initialization under Compute from Select VAWT Inlet Wind. Under Reference Frame, choose Absolute, click Checkmark Initialize Brain. But what does this mean? What is initialization? Initialization in CFD sets the initial values like velocity, pressure, turbulence quantities, etc. in every cell of the domain before the solver begins iterating. Think of it like giving Fluent a guess of what the flow field might look like at the start. A good initial guess helps the simulation converge faster and more stably. Why choose standard initialization? It's the most common method where Fluent assigns initial values based on one boundary, here, VAWT inlet wind. It pulls velocity, turbulence, pressure values from this boundary and spreads them across the domain as a starting field. This is better than arbitrary values like all zero, which can lead to divergence or slow convergence. What does compute from VAWT inlet wind do? Fluent uses the boundary condition at the inlet to calculate the initial velocity, turbulence, etc. for the whole domain. Since we set 10 meters per second at the inlet with 5% turbulence, these values will help create a reasonable estimate of how the flow begins across the model. What does absolute reference frame mean? We are initializing the flow field from the perspective of a stationary observer. If we had chosen relative, Fluent would interpret velocities based on a rotating frame, used in rotating machinery cases with moving reference frames. Since we already specified rotation in the cell zones, using absolute here is correct and avoids confusion. The model is now ready to run. First, save the project, file then save project to your working directory. Then run the calculation. Set number of iterations to 500, then click Calculate to begin the steady-state simulation. The solution will converge in just over 200 iterations. We've reached the end of this section. Hope you enjoyed it. Your comments, likes, and subscriptions really make our day and keep us motivated. Quick recap of what we did: set up the boundary conditions for velocity inlet and pressure outlet, configured wall motions for rotating blades using moving wall, copied boundary settings to all blade walls, selected second order, upwind for momentum and turbulence equations, used the simple scheme for pressure-velocity coupling, performed standard initialization from the inlet, saved the project and ran the steady-state simulation. Stay tuned for the next part.